for me and to stay here in this institute. And I have a small toy, is this one, you see in the picture, is this one, because it's late in the afternoon, so we are tired, so we have to do something. And so we can play with this small toy. So I will start with the motivation. The motivation is a biological one, and is to understand better what is the function of the heart. How can the heart pump blood in our body? So it's a fundamental question. And I have two movies here. And this is a real beating ventricle. And we are working with the medical doctors. And here you see in those reference, you see the name of the team is a team made of about 10 persons, cardiologists, engineers, mathematics and biology and so on. And you see the tracking of the motion. And in the other movie, you see a cross-section. So the same movie, but you see a cross-section, and you can appreciate how the thickness of the wall changes during the beating. And now I want to think about this, what's going on. So it's real and ongoing project. I don't know the answer, but I'm thinking about it. Pardon? Oh, red and green is the outer and the inner surface of the ventricle, yes. So I start from basic facts. And what is a muscle? A muscle is a solid, but a very special solid, because we have to control both force and position independent from each other. This is very important, because a muscle can be short or long and can sustain no load or a large load at the same length. And this is very important. Another very important issue is the second one. We think we use muscle to move, so we think that the muscle is a motor, an engine. But a muscle is also a brake, and is very important, the brake function of the muscle, because we have to control motion. And for example, if I raise a load, I use the muscle as a motor. But if I lower a load, I use the muscle as a brake. And it's very important, this aspect. And is very important also the second point, the third point, this point, that when we use muscle as a motor, we need a lot of power. So power is very important. And so we spend roughly 1.5 watt of metabolic power to have 1 watt of mechanical power, motor. If use the muscle as a brake, it's much more efficient. And this is the reason, it's very simple. This is the reason why we get tired when we go uphill, and we are not tired when we go downhill. So if I climb a mountain, it takes 1 hour, and I arrive at top, I'm very tired. Then I go down, and in half an hour I'm down, and I'm not tired. The mechanical work that my muscles are doing are the same. But the metabolic power is much more uphill than downhill. And then another important point is a muscle can only pull, so we cannot push. We can only pull. So now we have a question. When I have a muscle, that length, it pulls and it gets shorter, and now I recover the initial length. So I can go back. Then there are 3 types of muscle. Say, in the human body, there are 3 types of muscle, and they are called striated, smooth, and cardiac muscle. And if you look at microscopic level, the muscle, the motor unit is the same for such kind of muscle. And so here, now we comment about these facts. This is a spring, force position, 1-1-2 correspondence. And this is a muscle, so you span an area. And you have isometric exercise. You control the force at given position. And isotonic, you control the length at the given force. And this is the work loop. So when you move, when I work, when you run, whatever you do, usually you have a cycle, a work loop. And what happens in a work loop that if I raise a load, so increase the force, for example, and I shorten the muscle, like that, the muscle is a motor. When I go back, the muscle is a brake. So this is a work loop, a typical work loop for a skeletal muscle. And so the problem, how to recover the initial length. Skeletal muscle always acts in pairs. So you have one muscle is a motor, and the other, the opposite, is a brake, because you do not want this muscle to stay slack. So this is a brake, or it controls, but this is the motor. And so you can flex your elbow, and when you go back, now this is the motor. So you need to muscle. But there are some animals that have just one muscle, and they are called muscle. And this is the shell. Yes. And this is the shell. And the shell has another very important thing about muscle is what you eat. When we eat any kind of beast, we eat the muscle of the beast. And so we need the muscle of the shell. And this is a scallop, and you have only one muscle, and the muscle can only pull. So how to recover the initial position? Because you have here an elastic hinge, so it stores a lot of elastic energy. And so when the muscle releases, when the force in the muscle decreases, you recover the initial position using the elastic energy that has been stored. And here you know that here the muscle is a motor, and here is the brake. And it is not symmetric, this phase with respect to the other one, because you need this asymmetry in order to swim. So when you close, the movement is different with respect to the movement that you have when you open the shell. Now let us look at the cardiac muscle. Here you have a single cardiomyocyte, so it is made of a small number of sarcomere. And in this paper, there is a very nice experiment where they make a single cardiomyocyte work as a wool organ. And this is what they observe, so the work loop. So this is a diagram force length at the myocyte scale, so few microns. And this is the same kind of diagram. Here you have the pressure, and here you have the volume for the wool ventricle. And you always see a loop. And now the question is this a work loop, and what's going on? So for me, the most important feature of this plot is this one. So here you see, I use my finger because I want to focus you. I am changing the length by a lot at zero force. So something very weird is happening. And for example, a nematic isotropic phase transition, you change the length. There is a change of length. We have talked in the previous seminars about liquid crystal and nematic phases and so on. And so you have a change of length without forces. And here you have a change of volume, very large change of volume. And the pressure is decreasing for a portion of this increasing volume. So why? What is driving back the muscle? You don't have a skeleton here, so there are not two muscles, one against the other. You have only one muscle. And the shape of the muscle is very simple. It's an ellipsoid. So you have an ellipsoid, it gets smaller, and then it recovers the initial large volume. How it is possible? A simple explanation is it is the blood pressure, because there's blood that flowing from the systemic circulation, and so the blood pressure is enough to inflate this balloon. I'm a lot of doubts about this, because the blood pressure is very low. The thickness of the ventricle is very large, so we are talking about a vessel with a 1 centimeter thick. Is big like that, like my hand closed, and the thick is 1 centimeter. So is a very thick object. And the heart function, we run, we jump, we dive, our foot are up and the head is down, and everything is working. And it can beat 100 times a minute, 200 times a minute, so a lot. So there must be something else. And the idea is that there's some elasticity stored inside the muscle. So during the contraction, this part of the cycle, the heart is a motor, and is doing something like the scallop. So is changing the length, but it is also storing elastic energy. And then in this other part of the loop, it is a brake, and so it is controlling how fast the elastic energy is released, and so you can control the filling phase of the heart, which is very important. And now, here there are 3 pictures of the different kind of muscle. And so smooth muscle is striated skeletal muscle, and you see how well arranged it is. And this is the cardiac muscle. There are many striation, but there are also a lot of branching. And this is the sarcomere, and a sarcomere essentially is an uniaxial actuator. So the only thing that can do a sarcomere is to shorten, and then it stays short forever. You have to pull it again to make it longer. And the shortening is along one direction, and the volume is preserved. So when it shortens along this direction, the cross-section changes so that the volume is constant. And now I assume all these basic facts, and first of all, I want to model a solid that can control position and force independently from each other. And so we have to describe a change in the ground state of a solid, and there is a huge literature about this one, and in the framework of plasticity. So the idea is to use distortion. So to use distortion or pre-strain to model the ground state of a solid. And in this case, distortion are time evolving, so they change in time, so we can change the shape of the muscle. And the other thing is only pull, 3 types, uniaxial actuator. So what's going on? The idea is that those 3 types of muscle exploit different mechanisms to solve the problem of the push, how to recover the initial position. And we have hydrostatic skeleton for the smooth muscle. Usually we use smooth muscle around the vessel, and the vessel has fluid inside, so there is a pressure, and it is the hydrostatic pressure inside the vessel that function as a skeleton, say. Then we have the skeleton muscle, and there is a skeleton, the bone, and you always need at least 2 different muscle, antagonistic muscle. And then we have the elastic recoil. The elastic recoil, so you store elastic energy, and then you control the release. And for the scallop, is clear, it is like that. For the earth, we don't know. And now I explain the model. Elasticity with distortion. So the right picture for continuum mechanics with distortion is this one. I think is this one. So you have to look at a volume element, not a point, not a full body, but just a volume element, so a cubic element. A distortion is a tensor field, and it changes the shape of a volume element. So this cube is distorted onto this other cube. And if I have a general field of distortion, what happens if that you distort in different way different cubes, and then you cannot glue together the distorted cube. So you induce an incompatible distortion. And if you want to have a continuum body, you have to add further strain. And the elastic energy pays for this part of the strain. So the distortion is for free. This is a reference configuration of the volume element, and this is the ground state of the volume element. The volume element would like to be like that, but it cannot realize this configuration because it has to stay attached to this one and to this one. So you have to add further strain, and so you pay for that. And so you can describe this behavior, and the idea is that you have a fiber, and you map a fiber in a distorted fiber, and here you have the distortion. You embed the fiber in the Euclidean space, so you have the gradient of placement, and you pay for this difference. So you have a multiplicative decomposition. The elastic deformation is gradient of the embedding times the distortion to the -1. And so with the distortion, you describe a target metric. So a distortion field assign a target metric to a manifold. But you don't pay for it. You pay for the elastic metric. So you pay for Fe transpose to Fe. And so there is say a competition between the target metric and C is the metric of the embedding. And so the elastic energy is a function of the elastic strain. And now the point is I have a distortion, F0. This distortion induces a target metric. The question is this target metric realizable? That is, is there exists a placement and embedding that realize this target metric? So gradient F transpose gradient F can be equal to the target metric or not? If the answer is yes, it means that with a distortion, you can change the shape of a body. Also, you can induce a very large change of the shape for free without increasing the elastic energy. Because if this is true, then the elastic strain is the identity and the elastic energy is 0. So it is a ground state. So playing with distortion, you can induce a very large morphing. You can change the shape of a body very much, and the elastic energy stay constant or 0. It does not change. And so we summarize the natural metric, the metric of the embedding, the target metric, the elastic metric, the elastic energy. So it is very important to have a tool to characterize the target metric. So I want to know if this target metric is realizable or not without adding further strain. And there is an important theorem of differential geometry is you can express the curvature, the Riemann curvature, in terms of the metric. I give you a metric tensor, and you can compute the Riemann curvature. And if the Riemann curvature associated with that metric tensor is 0, then there exists there exists an immersion. So this configuration can be realized. And you can use this theorem to test the compatibility of distortion. So I give you a distortion, F0. I compute the target metric, F0 transpose F0. And then I test this target metric. So I compute the Riemann curvature related to this metric. And if I get 0, then that target metric is realizable. And so I have a change of shape for free. And here I have a nice picture of this is a famous painting by Esker, and it describes an hyperbolic metric. So the size of this figure is the same if you use the hyperbolic metric to measure the sides. And this, if you assign to a flat disk this metric, the disk does not remain flat. And you have such kind of configuration. And here you have the same, but for a ball. If you assign the same metric, so an hyperbolic metric to a ball, you get a stressed configuration. So the message is that for a surface, the surface is 2D, so you assign a metric that is not compatible in 2D, but the surface can exploit the full 3D ambient space, so you can change the curvature. And if your body is three-dimensional, you are at the top of the dimension. You cannot do anything but increase the elastic energy. And now I came with this small figure, and we can, I think, almost of us can understand what's going on here. So the problem is that you have a flat a distortion on a flat surface, a 2D manifold like this one, and the problem is that those four surfaces element, they are distorted in such a way that this angle here is larger than 2 pi. So I make a turn, and the angle is larger than 2 pi. So the only way to stay together is to have an hyperbolic saddle. So you have an hyperbolic surface, because this angle is larger than 2 pi. And the same, say, flat manifold, but now the angle is smaller than 2 pi. And so the distortion is not compatible with the flat. So this is not Euclidean. And the only thing that you can do is to realize an elliptic surface, so a paraboloid, like something like that. And so you understand the relation between, say, this angle, the curvature, and the shape of the surface. And now this small toy is to try to understand what's going on a 3D manifold. So here I have, instead of 4 surface elements, I have 4 volume elements, and they are distorted. And I want them to stay together, but they cannot stay together. And this distortion corresponds to an elliptic curvature. So the Riemannian curvature of this is not 0. And so if I want to fill this gap, I have to add further strain to the volume elements. And okay, let's go on. So the idea is to model 5 minutes. Okay, the idea is to model the functioning of muscle with the distortions, and so we have orthotropic distortion, so distortion with 3 directions, and also transverse isotropic distortion with just 1 direction, the same kind of distortion that we can use to model nematic elastomers. So in 1 direction you change the length, in the orthogonal direction you change the cross section. And so we can model a muscle using this kind of distortion. And this is what happens for nematic elastomers. And I will show you just as example a very nice result that we obtained a few years ago. And This is a bar made of nematic elastomers, and the elastomers lies in a vertical plane. And so here the axis of the nematic is horizontal, at the bottom is vertical. Then you have a phase transition, and you change from nematic to isotropic state. And so here is the lambda parallel and lambda orthogonal at the top of the beam. And so the top of the beam is long, and you have this bending. Then at this temperature, the two strain are the same, and the beam is flat. And then you keep on changing the temperature, and then now lambda parallel is smaller. And so the top is, and so you have a bending in the other, you change the curvature. And so you can describe with distortion this kind of behavior, very large change of shape. And you ask, is there stress inside this bar or not? And you can use this test. So you can, because this distortion lies in a plane, the Riemann curvature is very simple. It's just, it has just one component, and this is the component of the Riemann curvature. So you have to solve just one equation, and you say, and this equation says you that if the angle of variation along the vertical direction is this one, then the bending is stress-free for any configuration, whatever is the energy. So it does not care if the energy is Newton energy or whatever it is, and how large is the change in the length of lambda parallel or lambda orthogonal. You have, and here you have a different configuration realized with distortion, and so distortion changed the shape of this rectangle in this other figure, and all these configurations are stress-free. If you use a dopant to build that beam, you realize a linear variation of the nematic orientation. And so the black line is what you get when you fabricate the material. And the red line is the solution that gives you no stress. And it's very similar. So when you fabricate the material, you are lucky, and what you have almost the configuration of the nematic orientation that you need to get at zero stress for any configuration. I will skip, and I will skip these slides. And what happens if you play with the orthotropic distortion? So you can change the length along three directions. You can change the shape of a cylinder a lot. So all these configurations are stress-free. So you can change the length. You can rotate one base with respect to the other base, and these shapes resemble very much the shape of a beating ventricle. During the beating the ventricle, you have a change in length, a rotation of the apex with respect to base. Of course, you need a change of the volume inside the ventricle, and all these configurations are stress-free. So the idea is that you have such a kind of fiber architecture and the branching between the sarcomere to control the amount of elastic energy that you store during the beating. So you could realize a beating for free, but you can play with the say amount of distortion along three axes in order to store the right elastic energy that you need for the beating. And I stop, and this is a very nice, with last slide, a very nice picture that shows you the fiber architecture inside the myocardium. So those lines are the fiber of the muscle, and there are many connections between one line and the other. So the fiber structure of the myocardium is actually a 3D structure. So it is not, you cannot say that it is uniaxial actuator, but it has 3 axes because of the many branching that you see. Thank you for the attention. I stop here.